So welcome to radar engineering course. So we continue the discussion about the radar measurement here. So in a radar measurement, we say that when we send the signal from the device, okay, say that we have a radar here, and when we are sending the pulse to the object, so this is nothing but our object here. Okay, so we say that we have the object, and that to the object we supposed to send one particular transmitting pulse. Okay, so that is about a T out. We say that a T out, and that will be equal to what? R by C. R is nothing but what? A distance from this radar to the target, or whatever we can say that a object here. Okay. So now when the pulse reach to the object, then pulse will be reflected back from the object, and then we will get that a received pulse. Okay, so that is pulse will be reflecting from this object there. So we'll get that a pulse back. Okay, so this is a pulse back. The pulse back is depending upon that what will be the range and what will be the velocity of a light here. Okay, so that is speed of a light is considered that 3 into 10 is power 8 here. So means total time required for the pulse to reach to the radar is nothing but what? At what time we send the pulse to the object, and then it will be reflecting back to the object. So that is about a total time. Okay, so we can say that a that pulse transmitting from the device to the pulse reflecting from the object there. So that's why we can say that a transit time delay. Okay, so we can say that here a time required. Okay, so we can write here a round trip delay. Okay, so that round trip delay is nothing but what? A TR here is equal to what? What will be your a T back? Okay, and a T out. Okay, so whichever the pulse we transmitting, and a that is about repeating here. So we can write here is equal to T out and T back here, R by C. Both are nothing but a R by C here. Okay, so we can say that this R is about what we can say twice of R by C here. That is about a round trip delay. Or we can say that it is nothing but a total time. Okay, so that is about a time required to transmit the pulse and again receive the pulse. Okay, so that's about a total time required for this particular pulse. So from this we can calculate that what will be the range. Range is equal to what? What will be the speed of a light here? What will be the total transit time delay divided by a 2 here. Okay, so that is about your range here. So now from this range we can say that here the R. So we consider that from this radar, from this device, we send a pulse. Okay, it is visible to you all. Okay, so now we say the send the pulse from the device to the object. Okay, from this device to the object. That is about T out. Then object reflect that particular pulse to the device. That is about a pulse back. So total time, transit time. Okay, so what is the round trip delay? Round trip delay means what? Pulse transmission and a pulse reception. That is about a total time. That is about a round trip delay. So from that we can calculate the what is the range required. What is the range between the device and the object. Okay. So now here a pulse duration we need to consider always in terms of a microsecond here. Okay. So for that purpose, if supposed to we say that the total whatever the pulse we have. Okay, so pulse transmitting here. So I supposed to draw here now. So we consider that we have a transmit pulse. Okay, so this one is about your transmitting pulse. Okay, hope that visible to you all. Okay, this one is about a transmit pulse, and then we supposed to receive the a signal. Okay, this is about a transmit pulse now. You can say that a transmit pulse, and then this one is about our received pulse. So now this distance is nothing but what? A total transit time delay. And this is about what we can say that a receive pulse. Okay, this is about a transmitting pulse and this is about a receiving pulse. So that distance here is nothing but a total time or to hour. That is nothing but what? A twice r by c here. Okay, that is about a range here, range delay. So now we need to know about that. So suppose we consider that c here it is about a 3 into 10 power 8. Okay, now c is equal to what we can consider that a 3 into 10 power 8 divided by 2. And a tau we supposed to consider it is in the terms of a millisecond here. Okay, sorry, microsecond here. In that case, tau is nothing but a microsecond. That is, if we write in terms of a proper unit here, that is nothing but a 10 to the power minus 6. So that with respect to what? Just by a microsecond here. Okay, so this microsecond get cancelled. This one is about a meter per second. Okay, 10 to the power 8 meter per second. This one. Okay, so this is unit is about a meter per second. And if you solve it here, so we'll get that 150 tau a meter. Okay, so that is about a 150 tau meter. So this one is about a range. So this one is about a range. R is equal to what? N 150. That is about tau a meter. Okay, so this one is about a meter. So that is about it. So means we from this we can find out the range. Okay, the range simply using the what will be the total delay here. Okay, so that much suppose I am saying that a pulse delay is supposed to be 100 meters. Okay, 100 millisecond or 100 microsecond. So that is 150 into 100. So we will get that a total range direct. Okay, so this is about a factor here. So we will get the value is about a range in terms of this one. Okay, so directly we will calculate the range by multiplying the a range delays here. And that range delay, whatever we are getting, that will be in terms of a millisecond, microsecond. Okay, so whichever the factors or scaling factors supposed to be we are using, whether it is in a millisecond or a microsecond. Okay, so that is to be considered. So generally we supposed to use a microsecond factor to identify that what will be the a range here. Okay, so now this is about a final range. Now again a ambiguous range. So means ambiguous range is what? Whenever we are transmitting some particular pulse, okay, and then we are receiving some particular pulse. Okay, that is about a explanation. But a device, okay, whatever the device we have, that is an object or radar, it generally transmitting a pulses. It's not transmitting only a single pulse. It will transmit a single pulse. Means one pulse is transmitting. Okay, then after particular distance of a time, sorry, delay, after particular time delay, so another pulse will transmit. So means there will be a pulse repetition. Okay, so means we can say that pulse are transmitting with some particular a delay. Okay, so for example, I am saying here, this one is about what you can say that I'm just going to consider that this is about a transmitting pulse. Okay, so this one is about your transmitting pulse. We say it is about a pulse 1. So another time, another pulse is sending, that is about a pulse 2. Okay, width is same. Okay, just understand here. Width is same, everything is same. Okay, that pulse width is same. This one is about a pulse 3. Okay, pulse 1, pulse 2, pulse 3. Okay, now these are the various pulse. So, so what happened here? When device transmit a pulse, okay, this device transmit a pulse. So it is to be assumed that at t is equal to 0, that pulse is transmitted. Then we need to receive the pulse within a period, and that period is what? That period is nothing but what? It is to be received before the this second pulse is to be transmitted. Okay. So now I am saying that at t is equal to 0, that pulse 1 is transmitted, but we are receiving the second pulse after transmitting the another pulse. We supposed to consider that pulse 1 is received now. Okay, so I just consider that this much is about a gap here. So from this here, so we consider that this much is a time duration we supposed to require to receive the pulse. But now if you see here, so this one is about a time. Okay, that is time required to transmit the pulse from, I supposed to consider that it's supposed to be a T1 now. And we are receiving the pulse here, that is about a T2 now. Okay, for example. Now, transmitting pulse time and receiving pulse time, if you consider here, the pulse is received after transmitting the second pulse. But what happened here, the device will change the timing when it transmits the another pulse. So it is supposed to be considered that it will reset the device and then saying that it is to be transmitting the pulse at t is equal to 0. Okay, and then pulse will transmit. But after that second pulse transmitting, so we are receiving the pulse. So that's what happened here. So device will understand that this pulse will be received in between that t3 time, not this t2 time. Because device send the pulse, so then automatically that timing will start at t is equal to 0. So that's why, so the receiving pulse, whenever we say that pulse is to be received at this particular t2 time, but device will understand that pulse will receive at t3 time. Okay, so that's why whenever you are calculating the range, for example, I am supposed to be consider that a range equation right now. Okay, and we supposed to consider that range is to be calculated with respect to a particular distance now. Okay, so I am saying that this particular range. Okay, so how much is the, either we supposed to consider that a range is supposed to be given here, and from that range we supposed to find out that what will be the ambiguous time or ambiguous range. Okay, so for example, I supposed to consider that a t1 time right now. Suppose a t1 time. Okay, so how much is the t1 time required for that transmitting and receiving? This is about a distance between the two pulse, and this one is about a t2 is nothing but a transit time. Yeah, okay. So for this, we supposed to consider that about a transit time. So in that case, suppose I am saying that a object is at particular distance now. Okay. So in that case, we supposed to find out if, okay, as our formula, what is the formula? That is about a tau r here is equal to a twice r by c r. Okay. So now I suppose I am consider that a distance is here. Okay. I'm supposed to be consider that a distance is about a 90 kilometer, for example. So in that case, this will be what? 2 into 90, okay, divided by, this one is about 2 into 90 divided by 3 into 10 to the power 8. This one. Okay, after solving this one, so we are getting that is about a 600 microsecond. Means this T2 is nothing but a 600 microsecond. Okay, this T2 is nothing but a total time required is about a 600 microsecond. But okay, but what happened here? Because we supposed to consider that a pulse is to be transmitted. Okay, so that is about a difference between the pulse 1 and a pulse 2. Pulse will be transmitted at time t is equal to 0, and another pulse will be transmitted again. Device will take at t is equal to 0. But difference between these two particular pulses is supposed to be, I am saying that this difference is about a 400 microsecond. And we are getting that a 600 microsecond. Now there will be this T3 will be what? T3 will be of a 200 microsecond. Okay, T3 will be of a 200 microsecond. Now using this formula, I suppose to consider that a range is equal to what? Earlier we have calculated that 150 tau. So in that case, if I put that tau, that is about a 200 milliseconds, because device understand that pulse is transmitted at t is equal to 0 and then received. So in that case, it is to be received at a 200 microsecond. So tau, if I can put here, tau is equal to 200 here, 150 into a 200. Okay, 150 into 200. So if supposed to I am calculating this one, so I am getting that the distance or that range is about a 30 kilometers. And now this is nothing but what? A ambiguity in the range here. So here we say that range is about a 90 kilometer. Okay, I suppose to consider. But if we consider that a pulse is transmitting at t is equal to 0, this pulse 1, but if we are not receiving the pulse 1 before transmitting the pulse, we are receiving the pulse 2, pulse 1 after transmitting the pulse 2. So that's why there will be the range ambiguity. And now, if we supposed to consider that if that radar range, what we can say that R, okay, if that R is in between that whatever the pulse we are transmitting, okay, in between this particular range, means we transmit a one particular pulse and we supposed to receive the pulse before this particular transmitting pulse, then what we are getting, that range will be what? That range will be ambiguous range. Okay. But here what happened, if that spacing between the pulses, okay, whatever we can say that pulse transmitting from this and this particular pulse here, and that spacing will be a larger, then we will get the proper range. If the spacing will be a smaller, then we will get that unambiguous range here. Okay, so that is about, there will be the ambiguity to identify the pulse to be transmitting here. Okay, so what will be the ambiguous range here? That ambiguous range is depending upon that spacing between the pulses. Spacing between the pulses means what? Pulse 1 is transmitting. Pulse 2 what will be the pulse repetition interval here? Pulse repetition interval between the two pulses here. So that's why we can say that the R ambiguous here is equal to what? What will be the pulse repetition PRI? Okay, this is about a PRI divided by 2. Earlier we say that, okay, R is equal to what? Earlier what we have obtained, R is equal to what? A twice of tau R by C. Okay, twice of tau R by C earlier. But now the ambiguous range here, it is calculated if the spacing between the pulse is about a tau PRI, pulse repetition interval here. Then we say that there will be the unambiguous range. That unambiguous range of what? So C of tau of PRI by 2 here. Okay, this is about a unambiguous range. But if the target, okay, if it is less than that ambiguous range, then radar can measure its range unambiguously. Okay, means what? Before this particular pulse repetition time interval. Okay, and if that ambiguous range is greater than, okay, if the target range, this is about a target range, is greater than that ambiguous range, then radar cannot measure that range unambiguously. Okay, means what? If it is a beyond that particular pulse, okay, this one is about a delay, so then there will be the ambiguity to measure the that range here. So that's why we need to find out, or we need to know about that what will be the spacing between the a transmit pulse, spacing between the transmit pulse. So that spacing between the transmit pulse is nothing but what? A pulse repetition interval, RI here. Or we can consider that instead of that, in terms of a frequency, we can say that it is about a pulse repetition frequency. Okay, so that's just like we say that it is about what? Pulse repetition interval. Okay, or we can say that a pulse repetition frequency. Okay, okay, pulse repetition interval both. Okay, it is about a reciprocal here. Okay, so that is about a pulse repetition interval or a pulse repetition frequency here. So we can calculate in terms of a frequency also. Okay, so this way. So now what will be the pulse repetition interval or a pulse repetition frequency here? So this way we can calculate that a ambiguous range, whether that radar is able to find out that range unambiguously or is not able to measure that range unambiguously. So that's why to avoid that ambiguity, so that radar is to be designed in such a way that instead of sending the pulse, okay, we stop sending the same duration pulse. So we supposed to send that a group of a pulses or a pulse train. Okay, so instead of sending the simple single pulse, we supposed to send the a group of pulses. Okay, so now what are the group of pulses? What do you mean by the group of pulses? Means what? Here the pulse duration. Okay, so now this is about a pulse here. The in that case, we supposed to consider the a pulse train. Okay, and in which that pulse repetition interval will be different here. For example, I suppose to consider that a pulse 1 here. Now then another pulse. This is about a pulse 2 here. Okay, then a pulse 3 here. Okay, or we supposed to say that a pulse 4. Okay, so this is about a pulse 1, pulse 2. Now I suppose to consider that the distance between that pulse 1 and a pulse 2, I suppose to consider that a T1 here. Then distance between this and this one. This one is about a T2. Distance between 3 to 4. This one is about a T3. So in that case, a T1 is greater than T2 and T2 is greater than the T3 or vice versa. Okay. So in that case, we can measure that or we can say that T3 is to be greater than the T2 but not greater than the, okay, T3 is greater than the T2. Okay. Or we can say that but T3 is likewise. Okay. So in that way, we can consider that a T3 is greater than the T2 but a T3 is less than the a T1. Likewise. So we supposed to find out that. So in terms of a distance here, so this T1 always greater than the T2, but less than. Okay, T1 is always greater than the T2. T2 is less than the T3, but T3 is less than the T1. So like that. So we supposed to consider the group of pulses that is to be transmitting, and in such a way that we supposed to receive that a pulse within the particular period of a time. So here, because since we say that earlier example case, so we are receiving the pulse. Okay, so we say that this one is about a 400 microsecond, and then another pulse is to be transmitting. Supposed to be it is about a 300 microsecond, but pulse will be received. That duration will be what? A 600 microsecond in earlier, because 200 microsecond earlier. That's about a delay between the two. So in this case here, so we are able to identify that exactly. Generally, we say that this is about a 200 microsecond. Okay, this is transmitting. Okay, pulse here. So this way we can supposed to find out that A pulse we are transmitting, and we are receiving the pulse. Sorry, here we are receiving the pulse here. Okay, so this is about a distance about a 600 microsecond, and the delay we supposed to consider that apart from this, so this one is about a 200 microsecond. We are supposed to receive the pulse. Now this is 400 plus 300, so it is about a 700 because to receive the pulse, second pulse, it takes a more time. So that's why this way we supposed to use the rule, some rule to find out the or to avoid that ambiguity or to solve the ambiguity problem. That's about a range ambiguity problem. Okay, so now this one is about the way. So we need to pulse, we need to send a group of pulse, okay, or a pulse train, and that pulse train have the different okay time. Okay, so they say that start time is different here always, and we supposed to know that from the device they know that a distance between these two pulses here. Okay, so in that case, whichever the ambiguity will come will be reduced here. Okay, this one is about the another way to reduce the ambiguity in the particular range here. Then yeah, another way to avoid that ambiguity here. So instead of sending the single pulse here, okay, pulse repetition. So pulse repetition or a single pulse. Another way, same pulse is to be transmitting, but there will be a small variation in the phase here. Okay, so if we supposed to send a pulse with a different phase here, so in that case, so that ambiguity will be resolved, and this way we supposed to identify the whatever the distance prop- properly there. So what will be the minimum usable range here, so that we supposed to find out a proper range here. Okay, so in that case, so we supposed to transmit the pulse at t1, okay, t is equal to 0, and we supposed to receive the pulse here at some particular period of a time. So what will be the exactly a minimum range or minimum detectable pulse supposed to be considered that, and that is depending upon that a what will be the radar pulse width. Okay, so that we discuss later. So this is about the minimum detectable signal, okay, or that what will be the width of the particular pulse. Okay, everything we'll see, okay, later. Okay, so that's why there are the some different opinion about that what will be the minimum usable range and the maximum usable range. So for that particular purpose, we supposed to consider that a pulse is to be received from the target. So at t is equal to 0, okay, and because when we transmit the pulse from the object, from the radar to the object here, so radar will reflect the pulses here, okay, at different direction. So we need to know about that what will be the projection of this particular antenna, and which signal is received by this particular device here. Okay, so receiver, okay, when we transmit a particular pulse and another pulse is to be transmitted, this pulse 1 and a pulse 2. So when we are transmitting a pulse 1, t is equal to 0, at t is equal to 0. Then another pulse, again we are saying that at t is equal to 0. If supposed to be we are receiving the pulse after this, then there will be ambiguity. If we are receiving the pulse before this, then it will be work. For that purpose, we supposed to consider that a different train of pulses, and then we supposed to find out the range. Okay. Another issue is what? If we transmit a pulse T1, but we are not receiving the pulse, but we are able to receive the pulse at the time of it transmitting the pulse to here. So what happened here? A transmitter and receiver both are present in a single device. So circulator here. Okay, that is about use. And this one is about the antenna. So now when we transmit the pulse through this antenna, it will transmit. When we are receiving the pulse, at the time transmitter is switched off. When we are transmitting the pulse, receiver is switched off. It's supposed to be a time or that range. Okay, when we are calculating the range, in that case, when we are transmitting the pulse at the same time that receiver is off, if we are receiving the pulse from the object at that particular time when that receiver is off, okay, when the receiver is off, so then in that case we are not able to identify that whether that pulse is received or not. So that's why we need to know about what is the minimum range or minimum usable range, okay, so that that receiver is able to identify that particular pulse. If that receiver is off, okay, because during the transmission receiver is off, and at the same time supposed to be pulse is receiving, okay, then we are not able to obtain that particular range here. Means we are transmitting the pulse at t is equal to 0, and we are sending the pulse, okay, at a t is equal to 0, transmitting pulse. At that time receiver is off, and then that device is supposed to be considered that at t is equal to 0. Okay, timing. Okay, so t is equal to 0 means pulse is received at t is equal to 0. That is about the ambiguity. So that's why we supposed to find out that what will be the minimum usable range here. So minimum usable range is equal to what? Okay, what will be the a radar pulse width? Okay, this is about a whatever the radar pulse width is. Okay, so this one means we say that here the pulse is received. If we say suppose to consider that if that pulse is receiving by the receiver, okay, at a means we can say that we send a particular pulse to the target and it is to be received by the receiver here. Okay, so in that case we say that a pulse is received before transmitting the pulse. Okay, another pulse. This is about a second pulse. Then we are able to find out that the R here. So in that case, so what will be the minimum time? Okay, minimum time required because we have a device, there is a display, okay, that processing, everything is there, okay, in a radar. So in that case, so what will be the minimum time required to identify or do the calculation at that particular area so that we are able to find out the range? Okay, so that is again the issue about the a range measurement. So we are not able to find out the exactly, okay, so on the display that particular object there. Okay, so we supposed to consider that that receiver is to process that particular signal if it is a or if that object is near to the radar there. So that's why we supposed to find out that what will be the particular pulse transmitting here and at where when we are receiving the pulse, whether after transmitting the second pulse or before transmitting the second pulse. So that's why we supposed to find out that what will be the minimum and a maximum usable range here. Okay, maximum usable range here, that is nothing but what? One pulse is transmitting. Okay, so we can say that what will be the pulse repetition time minus, because it is with the before transmitting the pulse, it is to be receiving there. Okay, so this one is about what time here the range that receiver is off, and this one is about the range here, that is about a range that will give that one pulse width before the next transmit pulse here. So in that case, this is about a window, that is R minimum and R max. It is about a processing window. Okay, so this about processing window, we supposed to find out that what is the maximum visible range, okay, in which that radar is to be operative. Okay, so this is about a issue to find out the a radar range here. Okay, so that's why we supposed to use a Doppler frequency measurement. Okay, so other factors to be considered to measure the radar range. So we'll see in detail, and in this case, we supposed to find out that what will be the minimum uh, detectable signal is required. Okay, so we'll go in detail again. So before that, we need to see that what is the radar range equation. Okay, and then we come again to this particular topic again, and then we can find out that a radar. So already we discussed that whatever the unambiguous range here, with respect to that, earlier we say that a pulse repetition time, PRI here, interval here, pulse repetition interval divided by 2. Okay, so or we can write here another way, F here. Okay, in terms of a pulse repetition frequency. Okay, so we can write into both the way, either pulse repetition frequency or pulse repetition interval. Okay, so this way. Next, we talk about that what is the simple form of the radar equation. Here, we talk about that what is the radar equation. Okay, so radar equation, we supposed to know that what will be the power transmitted by this device. Okay, means radar, we have a transmitter there, and what will be the transmitting pulse? Okay, what will be the transmitted power by this radar transmitter there? Okay, so to identify that, what will be the power transmitted by the device there? If we consider that a device is supposed to be a standard antenna, generally we supposed to consider that any antenna, that antenna is to be a directional one, highly directional antenna. And for the given highly directional antenna, so we supposed to get the a beam, narrow beam, so that whenever that object will reflect the signal, so we supposed to receive the pulse properly there. Okay. So to identify that, what will be the transmitter we supposed to use, or transmitting antenna we supposed to use? What will be the receiving antenna or receiver supposed to be we are using? Okay, transmitter, receiver, antenna, and then because we have a device radar, so it has a transmitter and receiver both are there, and both are connected to the single antenna. Okay, this one is about a single antenna, and then we are supposed to consider that there is an object, and that object we send the pulse here to the object, and then pulse is received by this, reflecting by this particular object here. Now we talk about that. So what will be the transmitter, what will be the receiver, and what will be the antenna we supposed to be used here in this particular device here. Okay, now these are about the component of the radar, and through that we supposed to calculate that what a radar range. Okay, or a radar equation. Okay, so to consider here we supposed to consider that a device we say that antenna is about the isotropic antenna, because isotropic antenna radiates the signal in all the direction there. And then from that isotropic antenna, what will be the power density at distance r? Okay, at a distance r here from the radar, that is depending upon that what will be the transmitted power, okay, transmitted by this particular transmitter here, and what will be the surface area, okay, total surface area that is to be, because we say that this is about isotropic radiator. It radiates uniformly in all the directions. Generally, we're supposed to consider that a point source now. So this is about a source. So it radiates uniformly in all the directions. In that case, what is the distance? Okay, so this is about all the directions. That's why we can suppose consider the circle here. So in that case, it is about a 4 pi r square here. Okay, this is about a circle. So in that case, a power density from the isotropic antenna, okay, power density from the isotropic antenna is equal to what will be the transmitted power divided by 4 pi r square. Okay, so r is about what? Generally consider that imaginary sphere. Okay, so this is about a sphere. So this is about a, okay, one particular sphere. So that's why we are supposed to calculate that a power. So generally in a radar, we're supposed to use a highly directional antenna instead of a isotropic antenna. We're supposed to consider that a highly directed antenna. And that highly directed antenna means what? It directs the signal in only one direction. Okay. Okay. Whatever the power is transmitted by this device through the antenna, it will be directed toward only in one direction. Okay. Or in particular direction. Generally toward the object. So in that case, we need to know about that. What is the gain of an antenna, whichever we are using here. So instead of consider the isotropic antenna, isotropic radiator, we're supposed to be consider that a antenna, and that antenna gain we're supposed to know that. And that antenna gain is nothing but what? What will be the power radiated in the given direction? Okay, and that is to be compared with to be isotropic radiator, so that we'll get the gain of an antenna there. Means it is nothing but what? It is the ratio of maximum radiation intensity, okay, to the particular direction there, and to the radiation intensity from a lossless isotropic antenna there. Okay, so that's about a power density from that is about the gain. So we can calculate the power density of this particular antenna there. So with this, we stop here. We'll continue the discussion next lecture. So thank you all of you.